Hello and welcome to our Limbus sessions. You're going to find that throughout the semester these will come in very handy as you are reviewing for exams, trying to get a better grasp on the material, and maybe just filling in some of the gaps that you may have missed even during lecture, or maybe you couldn't make it to lecture and so therefore you're using this as a means of catching up. Maybe. Welcome. This is Professor Young, and this is Anatomy and Physiology 1, Chapter 1, starting at the beginning. And as you recall from the lecture, I began really discussing, or at least throwing the question out, why in the world would we want to study anatomy and physiology together? Anatomy by itself is overwhelming. Physiology by itself is overwhelming. And when we combine the two, we have double the overwhelmingness. And so why? Why take the time to be able to really go through and study both of these complex topics at the same time? And I suggested that it came down to a very simple analogy. You would not take your car to a mechanic who could identify and point out every single nut and bolt and part of your engine, but had no clue how they related to one another, have no clue or has no clue exactly what the structures do. Instead, when you take your vehicle to a mechanic, you're expecting that not only does that mechanic know the parts, but that they also know how they work. And beyond that, how they relate to one another. And that's the point of studying anatomy and physiology together. To not only say, yes, this is the heart, but being able to say, this is the endocardium, this is the myocardium, this is the epicardium, this is a myocyte or a cardiocyte, this is this structure, this is that structure, this is the interventricular septum, and within here is the conduction system, and this is the part of the conduction system, the bundle of his, and this is what that does, and this is how it relates to the overall structure of the heart, that being the left and the right ventricle. You want to be able to not only say in a picture or a diagram or a specimen, that's what this is. But as you say, this is the right ventricle, you want to be able to have a picture developed in your mind of what is happening physiologically within that structure. It's exactly what a mechanic does when you bring your car to the mechanic and you pull up and you say, hey, it's not working. This is the sound it's making, or boom, 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 boom. You're describing a sound and you're expecting your mechanic to say, oh, geez, that's what's wrong with your car. The bum, 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 bum is really this. That's what you expect, and that's what we expect out of you when you study anatomy and physiology. When you see that symptom, when you see that structure, what's happening? What's the underlying structure or framework, biochemical, physiological framework that is really upholding that structure? And so it's really very straightforward and simple. Why do we study anatomy and physiology together? Because when we do, we get a complete picture of what is really happening within that structure. Look at the basic definitions here. And again, these are the basic definitions. What we're really talking about here is the study of the structure. What does it look like? What are the parts made of? As you're going through and studying your various bones of the body, you're studying the structure. That's all fair and good. That's all nice. It's all pretty and packaged and easy. Right? But what does that structure do? How does that structure relate to other structures? And that's where the learning begins. Why is the magnum foramen where it is. Why does C1, cervical 1, the first vertebrae, the atlas, why is it positioned where it is? Why does C2, or the axis, the second vertebrae within the cervical column, why does it have this funny-looking protrusion that sticks up into the foramen magnum? And why does it sit like it does on top of C1? What does that do? And when we talk about that, we start to get at the heart of physiology. We start to answer the question of what is the function? What is the function? Physiology looks at the function of something very often, not always, but very often on a biochemical level. It can also be at a cellular level. It doesn't have to be biochemical. It can be at a cellular level. But when we look at that function, then we begin to understand this true structure. We begin to understand what it means when we say the occipital crest. We begin to understand when we say the right ventricle. We begin to understand when we say the ilium or the iliac crest or the myocardium versus the endocardium versus the epicardium. We actually put true understanding to that structure. And we begin to run animations through the head of what is happening as we say these structures and these names. Keep in mind that the driving force for anatomy is the physiology. Pay attention to what I just said. The driving force for anatomy is the physiology. It is the physiology. In other words, what I'm saying when I say that, right, is this. This is what this is all equaling. What I mean by that is function dictates form. Function dictates the form. If you want to know what something is going to look like, you've got to go deeper into how it functions. If you want to understand why something looks the way it does, you've got to look at the function. And if the function changes, the structure is going to change. Maybe not overnight. Maybe not within a generation. We might be talking 2 or 3 generations. We might be talking 6, 7, 800, 900, 1,000 years. But eventually, the structure will catch up with the function. What something does dictates what it looks like. I'll give you a quick analogy about this. You've got a meth addict. Right? They're doing meth. They're dropping meth left and right. Every 4 hours, they're taking a hit of meth. There's the physiology. There's the function. They live to do meth. Look at what the meth does to the structure. Rots the teeth, gum disease, the loss of hair, the skin tone, the jaundice appearance, the extreme weight loss. The physiological function of what's going on within the body impacts what the structure looks like and how it behaves. Now, that's a very startling visual concept, and I understand that. But that's what's happening right here down deep below. So to know the parts, you're missing a half the story. To only know the function, it's impossible. You have to know the parts in order to know the function. The two are so intertwined with one another that you cannot possibly separate them. And most of what is happening here is happening at that physiological level. It's happening down deep within the cellular level of the structure. And the whole reason why we have this very intricate dance of interaction between the function and the form is for one purpose only, and that is to maintain homeostasis. Homeostasis is the reason why we have function and form. Homeostasis is the key. Homeostasis is the number one word for anatomy and physiology. What is it? Homeostasis, in the simplest terms, is about maintaining balance. It's about keeping the body and its functions within a range of acceptability. It's about keeping the body in a range of functionability. Functionability. That's not really a word. Therefore, I'm not actually going to type that and put that on this. It's about keeping the body within a range of functionality. Functionality is a word. It's about keeping the body moving. That's all homeostasis is about. The problem is, it's very easy to knock the body out of homeostasis. It's very easy to knock the body out of or beyond the upper and the lower limits of the ranges. Body temperature, 98.6. We all know that. Does that mean if it's 98.7, you've got a fever? And if it's 98.6, you've got a fever as well? Or 98.6 if it's 98.5? Does that mean you're running a low-grade fever? Does that mean you're going to be hypothermic and we've got to wrap you in blankets and shove you next to a fire and warm you up? No. It's because body temperature, why we say it's 98.6, it's really a range. It's really a range. 97.9 up to about 99.1, somewhere around there. There's the range at which the body can function. And even that range varies from person to person. Everyone is different biochemically, and therefore everyone's range of homeostasis is also going to differ. With that said, once we have exceeded those boundaries, the lower and the upper limits, once we've exceeded that, we've entered into the pathological. We've entered into a state where the body cannot maintain homeostasis. Normally what will happen is the body gets knocked out of whack and the body can compensate for that relatively quickly. No harm, no foul. Everything is good. But we know all too well that sometimes the body cannot recover and bring the system back into a balance. And it stays outside of those upper and lower limits. And that's where we enter into disease. Dis-ease. Think about the root and the prefix here. Disease. Cut that word in half. On the first part here, we have dis, which means not. And on the second part, we have ease, comfort. Not in comfort, not in balance, not within the norm, not easy, uncomfortable. That's what disease is all about. Disease is about not being within the norm. And so the body has to find a way to try to maintain it. If not, then there's other serious steps and actions that can follow. There's a multitude of different paths for which that can go. The other thing that you need to consider is that when we talk about maintaining homeostasis, and we talk about this at a cellular level, that we also need to consider the surface and the point of contact at which the cells can do this. How much of the cell can actually be involved in the regulation of what is happening? And if you look at my pretty little picture here, I'm exaggerating on pretty little picture, but that's okay. You will notice that we've got this huge area right in here of a cell membrane that's in contact with other cells. Maybe there's a little bit of space every now and then. In other words, if I was to start plopping in cells, here's a cell, here's a cell, there's a cell. You get the picture. That's surrounded by other cells. The other thing to consider is the fact that in between here, we've got empty space. We have empty space. We have empty space. What we call extracellular material. What we call interstitial space. All of this area provides limited contact with the outside environment for the cell and for the cell to be able to maintain homeostasis. We'll have a little bit in here, but not much. It is in fact right here where we have all of the contact. It is right there where we have the ability for homeostasis to be maintained. That is where the cell has the maximum ability to get rid of waste and to bring in nutrients, to remove carbon dioxide and bring in oxygen, to bring in water and remove a buildup of ions that could be toxic. That's it. Right there. Not a whole lot. The way homeostasis is able to do this, in other words, the way we are able to maintain homeostasis within the body, is really a series of chain reactions. And those chain reactions start with receptors. Things that are going to be there to collect data from the outside environment, whether that's literally the outside environment, the air around your body right now, or whether that's the interstitial space surrounding the cells. Whatever the case may be, it's external either from the cell or from the organism. And those receptors that are located on the cell membrane, the receptors that are located on the organs, those receptors that are located within the systems, those receptors that are located out on you, are constantly collecting data from their environment. And what they're doing with that data is sending it to the central nervous system, the control center. The stimuli being collected from the receptors are being funneled down into the central nervous system, and the job of the central nervous system is to control what the response is from the body. Do we need to react to something? Do we not need to react to something? Here's where normal is, quote unquote, the set point. Here's what the information is telling me. Is this a situation in which the body needs to respond? Are we out of homeostasis or are we in homeostasis? Once the central nervous system has been able to get a grasp on that, Then comes the response in the form of an effector. In the form of an effector. It is what's going to give the response. The air temperature drops outside dramatically. It drops 40 degrees in a matter of an hour. You're outside in shorts and a t-shirt. The next thing you know, it's cold. It goes from 90 degrees to 50 degrees. And that cold air is going to be, that sense of change from the environment is going to be detected by receptors on the skin, which is going to send a stimulus to the central nervous system. That's going to say, it's cold out here. My inner core temperature is dropping. And that control center is going to send a response through the effectors that's going to say, shiver. Get those muscles twitching, which is going to generate heat. And that generation of heat is going to raise the central temperature, the core temperature, and it's not going to seem as cold. That's how homeostasis works. For those of you that like pretty pictures, here's a pretty picture. And you can see in this picture, up top here, the organism is happy. It's in homeostasis. No complaints. Then all of a sudden, there's a change within the environment. There's a change within the environment. Whether it's an external change or whether it's an internal change, something has thrown homeostasis beyond the upper and the lower limits. And so now the body needs to react. It needs to overcompensate for the change to bring it back into normalcy, to bring it back into the range of those upper and lower limits, to bring it back into, you guessed it, homeostasis. If it works, great. If it doesn't work, and it continuously doesn't work, then we end up on this side of the chart. And that's not where you want to be. An example I gave you in class. You're sick. It's a bacterial infection going through your body. Maybe it's pneumonia. Maybe it's a little bit of strep throat. Maybe it's a severe sinus infection caused by bacteria. And now you've got ear infections and your throat's infected and it's swollen and your eyes hurt. You go to the doctors and the doctor puts you on antibiotics. The antibiotic, probably some derivative of penicillin, amoxicillin, probably, acts as a shotgun. It's a broad-range treatment. It's going to shoot and kill anything in its sight that's bacterial, good or bad. That causes a change within the environment. And the example we went over was one of the vaginal cavity. The vagina has a low pH. It's an acidic environment, typically ranging anywhere from about 3.5 on up to a 5 in pH. What causes that is a bacteria. It's a good bacteria. Lactobacillus, acidophilus. Right. Acidophilus is a member of the lactobacillus family. So the lactobacilli is an entire group or genre of bacteria. And it's living down within that vaginal tract. And lactobacillus, lactose, it's breaking down sugar. And as a means of breaking down that sugar, it's releasing lactic acid. which is creating the acidic environment down within the vaginal cavity. Well, good old lactobacillus, being a bacteria, even though beneficial, when taking a very broad spectrum antibiotic, gets knocked down, gets wiped out. The decrease in the presence of lactobacillus is then going to decrease the release of lactic acid, which is going to cause an increase in vaginal pH. It's going to cause an increase in vaginal pH. When we do that, we give other things that may not be bacterial a chance to grow. What, and pray tell, may I be talking about? Well, I may be talking about a fungus known as Candida albicans, which is there. It's normally there within the vaginal cavity. The difference is it doesn't like low pH. It doesn't like acidic environments. And so it's kept under control by the presence of lactobacillus, which is doing fermentation, breaking down sugar, releasing lactic acid, lowering the pH. You're taking antibiotics, broad spectrum, boom, 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 knocking out everything in its sight, including lactobacillus, decreasing the population of lactobacillus, which decreases the rate of fermentation, which decreases the breakdown of sugar, which decreases the release of lactic acid, which increases that vaginal pH. Candida albicans now has the opportunity to grow. The cat's away, the mouse will play. And in this case, the mouse, Candida albicans, will grow into a yeast infection. The body needs to be able to overcompensate that. Now, unfortunately, the only way the body's going to win this war is if you stop taking the antibiotic. Or if you supplement with the antibiotic something that have probiotics, something that is already inoculated with live cultures, something like yogurt, which normally helps to replace the lost lactobacilli to be able to maintain a low enough pH to keep Candida albicans at bay. That is how this all comes together and works. Kind of quickly just kind of going over this slide here as we transition. Now that we understand homeostasis, we keep talking about the fact that it happens at the cellular level. Well, what do we mean by that? We know what molecules are. We know that molecules are made up of atoms that are joined together. These molecules, when joined together in a specific grouping or structure, can form organelles. Organelles carry out a specific function within the cell. And when we group these organelles together, organelles that create energy, organelles that transport energy, organelles that build support structures, organelles that carry out the overall blueprint for what's going to be happening, organelles that clean up debris, organelles that create energy, organelles that move things in and out of the cell. When we combine all of these organelles together, we form a cell. And the key here with the definition of a cell is simply that it is the smallest unit of an organism that carries out all the functions of that organism. That is what a cell is. A cell, a unicellular organism, can pretty much do everything that you can do, except maybe on a simpler form or a simpler scale. We take those cells and we take this cell type over here and we take another cell type over there and we take another cell type over here and we group them together, and those cells are working together to do a common goal. We have ourselves a tissue. Cells that are carrying out a specific function. And we take a tissue type from over here, and we take a tissue type from over there, and we collect this tissue type over here, and we join them together. And those different tissue types are carrying out a specific function. We call that an organ. And when we take an organ from here, and an organ from there, and an organ from there, and they begin to work together, we create an organ system. And we take collectively all of those organ systems, all 11 of them, and they begin working together. And in our case, we create a very complex, unified, single organism. What defines whether or not that organism can truly be defined as an organism is based on these 8 very simple characteristics of all living things. If one of these criteria is not met, you are not dealing with a living organism. All 8 characteristics must be met in order to be considered living. And that is critical. If an organism has organization, if it's made up of cells, if it can do metabolism, if it can react to its environment, and if it can maintain homeostasis, and if it can grow, and if it can evolve, but it can't reproduce, then it's not living. Not being able to do one of these 8 characteristics knocks it right out of the grouping. That's why viruses are not living. Viruses have organization. Viruses are not made out of cells. Viruses can do metabolism. Viruses can react. Viruses cannot maintain homeostasis. They can develop, and they can evolve. But they're not made of cells, they don't have homeostasis, and they can't reproduce. Viruses aren't living. It's that simple. So again, what is critical here is that all 8 characteristics must be met in order to be considered living. That is critical. When we talk about organization, it's exactly what we looked at on the previous slide. It's the exact same thing. We know what cells are. Every living thing must be made up of at least one cell. When it comes to metabolism, understand that we've got 2 types. We have anabolic and we have catabolic metabolism. With anabolic metabolism, what we are really referring to here is building molecules. And when we deal with catabolic metabolism, what we're really dealing with is breaking down those said molecules. Anabolic is building molecules, it's storing energy. Catabolic reactions are breaking down those molecules, they're releasing energy. Reactions that are happening within the body are put together, and the sum of those reactions is what we define as being metabolism. It is the sum of all reactions. That is the definition of metabolism. All living things need to react to their environment. They need to respond. If it's too cold, you got to get warm. If you're too hot, you got to get cool. If you're hungry, you got to eat. All living things need to maintain homeostasis in some way, shape, or form. All living things need to be able to develop. Even the smallest of bacteria, which develop through or which reproduce through a process known as binary fusion, poof, they're formed. They split off. And voila, you've got two new, even those newly little formed bacteria need to grow and develop into big mature bacteria. All living things need to be able to reproduce. And most importantly, all living things must evolve to their environment. They need to adapt. That's what evolution is. Evolution is a response to the environment leading to adaptation. Those that are better able to adapt and change to a changing environment are going to survive. How do we do all of this? How are we able to do homeostasis so that we can develop and reproduce? How do we maintain homeostasis and the energy that is needed? Through metabolism. When we get so far out of homeostasis, how does that relate to our ability to react and adapt? The answer to all of those scenarios are found within the concept of negative feedback. This concept of when we get knocked out of homeostasis, or when we get knocked out of dynamic equilibrium. Equilibrium, being at level, being equal. Dynamic, though, means that there is a change that can take place, and you can still be considered equal or normal, quote unquote. Dynamic means there's movement that's able to have happen. If it was static equilibrium, 98.6, bam, boom, that's it. If you're 98.6, you're equal. If you're not 98.6 for your temperature, you're out. That would be static equilibrium. Dynamic equilibrium, on the other hand, says there's some cushioning. Says there's leadway. It says there's room for movement. And you can still be considered normal. What negative feedback does is it detects when you're beyond that range. It detects when you're beyond dynamic equilibrium. And it sucks you right back in. You're trying to get out of the bounds, but negative feedback responses pull you back in. They reverse the changes that are happening so that you maintain, quote unquote, normalcy. that pink blob isn't going away. But if you look at the actual slides that I have posted on Ocean Cruiser, you will see, I never took it off, sorry, but you will see that, A, B, and C, A is the normal, B is the stimuli, C, things start going awry, D is the response to the change that we see in B. What a negative feedback will do is, if we could pull off that pink square and look underneath of that box, what you would see is that there'd be a little arrow that comes on up right here, and it basically removes that stimuli. And when you remove the stimulus, you remove what's bringing you out of homeostasis, and you bring the body back into normalcy. It's the same thing right here. It's a back and forth. Your body temperature goes up. You got to cool yourself down. Vasodilation. Open up the blood vessels. When you open up the blood vessels, you allow more blood to reach the surface area. When you do that, you bring more blood to the surface. You release more heat. As you release more heat, you cool down to bring yourself back down to normal. But then sometimes it goes too far and you get cold. And so you vasoconstrict, your blood vessels tighten up. And that reduces the amount of blood flow going to the surface, and it creates heat within the inside. And as you create heat within that inside, your temperature goes back up. And then you get too warm. It's kind of like a hot flash. How you can be sweating 45 seconds ago, and 45 seconds later, it's like you're in an ice box and you can't get warm. And then 45 seconds after that, you're sweating again, wishing you were back in the ice box. And guess what? A minute and a half later, your wish has come true. You're back in the ice box again. That's what hot flashes do to you. Go back and forth, back and forth, back and forth. It's your body trying to overcompensate for changes that are happening so quickly within the body that it can't keep up with itself. But it manages. All right, I'm not going to go over that. Not going to look at that. You can look at that on your own. The opposite of negative feedback is positive feedback. Now, positive feedback is not always a good thing despite the name positive. Negative feedback is not always a negative thing despite the name negative. In fact, negative feedback systems are typically a good thing because it brings you back into normal. What positive feedback does is the body says, oh, there's a change. I'm going to respond. And that response, instead of stopping the change, says, keep going. You're doing just fine. And it drives the body further out of homeostasis. It's what we refer to as, and this is a key term for us, self-amplifying. It is a self-amplifying response. In class, I gave the example of the process of birthing. In order to get that football out of you, that little bundle of joy, that fetus that is ready to come out, the uterus needs to contract. What causes uterine contraction is oxytocin. And so the uterus goes ahead, it begins to contract, it puts pressure on the baby. That baby starts stretching everything out in the cervix, and the cervix sends a message to the brain that says, ouch! The response from your hypothalamus is send more oxytocin. Oxytocin is then released, it goes down to the uterus, and it causes the uterus to contract more, which puts more pressure on the fetus, which causes more stretching. And that more stretching down within the cervix sends more pain receptors up to the hypothalamus, and the hypothalamus says, ouch! And it releases more oxytocin. More oxytocin equals more contraction of the uterus, which equals more force pushing on the fetus, which causes more stretching, and that baby's coming out. It's coming, it's coming, it's coming. The problem is you've got all this oxytocin built up within your system. That's positive feedback. The system keeps going. You're so far out of homeostasis that it takes about a day, day and a half for those oxytocin levels to begin to fall. And when it does, that's where postpartum comes into play, when all those hormones begin to fall out. That's where the mood swings, and I say that very carefully and respectfully. It's where all the mood swings start coming in. It's why mothers start crying about 2 days after birth. And they don't know why they're doing it, but they're doing it. It's because all these hormones that were spiked way up above homeostatic levels, poof, the floor has dropped out from underneath of them. And the body's got to now scramble through negative feedback systems to try to raise them back up to a level that's normal. And then here we go. All right. Final thought, and I know I'm a little over time here. I try to keep these to about 40 minutes. But final thought. When we really look at what we're doing here in anatomy and physiology, what it comes down to is really a threesome, for a lack of a better term, between biology, chemistry, and physics. It is the perfect marriage, albeit a threesome, between these three disciplines of science. Without understanding fluid mechanics and without understanding what the impact of fluid mechanics are on vasodilation or vasoconstriction, and without understanding how vasoconstriction and vasodilation within the circulatory system impacts the wall and the lining of your arteries and your vessels and your veins and your capillaries, you don't have a complete picture. Physics and chemistry are going to have, that's your physiology right there. The chemistry and the physics is what is happening. It's the function, the physiology. Without having an understanding of that, the biology, the structure, just isn't going to make sense. You're in for a ride this semester and next semester as you go on to A&P2. Really looking at everything that we have looked at this first night here in lecture. You want to pay attention to the themes. How is the function of our body impacting and dictating the structure? Where is the biology, the chemistry, and the physics intersecting? The point at which they cross is the point at which we have homeostasis. And that is the basic tenets, everything that you're going to learn in anatomy and physiology. With that said, if you have any questions, if you're not sure of anything, send me an email. Jot the question down, ask me in lecture. My number one concern is that you understand and appreciate the information that we are going over this semester, and that you leave the course with your answers, with your questions answered. With that said, have fun studying. I'm here to help you. Shoot me an email. And this is the end of your first little old WIMBA session. Many more to come. I wish you all good luck, a great semester, and again, I'm here if you need me. Shoot me an email.